I'll get started. Let me begin with a word of prayer here. Dear Father, we thank you for this day. Again, I thank you for these students, this class, and this wonderful cold weather. Help us to glorify you today in what we do, and just understand a little bit more about springs and things, Lord. In my prayer, Lord Jesus. Amen. So I will let you guys look at the solution to the team mission here over the weekend, and then come Monday we've got a day to talk about anything that's still confusing, and perhaps we'll also have time today once I'm done with this derivation I got to go through here. So today I want to talk about a slightly more interesting problem perhaps, and that's the problem of resonance. And so just to set up the problem, here's the problem. We're going to look at basically m x double dot plus b x dot plus kx equal to f naught cosine of gamma t, and we're going to assume that b squared minus 4mk is less than 0. All right, and the question we want to ask and answer is, what choice of gamma results in like the largest amplitude, the steady state solution with the largest magnitude for a given force, right? So the idea here is that you've got a spring, right? and then there's a mass, right? And then you got Mr. Top Hat over here, and he's pushing and pulling on this thing that's in oil, right? Whatever. However you want to think about the friction coming from. I'm just going to stick it in oil because it's just what I do. But M, K, and this guy, it's got B, right? And you're applying F naught cosine gamma T to the system, all right? Then the question is, which choice of frequency gamma maximizes the resulting motion? Do you guys understand the question? So what makes this different than other problems we've solved is, well, it's got lots of letters, for one thing, right? So it's like your one homework problem that I inadvertently solved in class. Sorry. But you know, it's also related to the problem we did at the end of last class, right? Which was in the case that we didn't have friction, right? And we just, you know, pushed on a mass without friction, with the same frequency as the natural frequency of the spring, we saw that the motion's unbounded, right? But here it's a little different. Now, if you don't know, I don't know if you knew or not, but this is another notation. This is a historic notation. X dot is dx dt. X double dot is d squared x dt squared. This is Newton's notation for time derivatives, all right? The notation we usually use is Leibniz's, obviously Leibniz 1, right? Apparently. But I would guess if you were to do a survey in the general population, as long as we're not in France, like who do you know more, Newton or Leibniz? I'm guessing Isaac Newton wins in the battle of science celebrity. But all right, so let's get to it here. So we've got m lambda squared plus b lambda plus k equals to 0 for my characteristic equation, which of course gives me, well, I'll just get straight to it. It gives us lambda is equal to minus b plus or minus I times the square root of, oh man. Oh, no, I'm fine. I'm just, we did this last time, so I'm not trying to go through it again. I think this was it. This is the what case is this? underdamped. That's right. So this means that my homogeneous solution, right, looks something like C1 e to the minus b over 2m t cosine of the square root of 4mk minus b squared over 2m all times t plus C2 e to the minus b over 2m t times the sine of the square root of 4mk minus b squared all divided by 2m times t. I should have given this thing a name, you know. I should just call this, I should just say this is like minus b over 2m, you know, plus or minus I like omega naught, you know. And if I did that, then my solution would just be C1 e to the minus b over 2m t cosine omega naught t plus C2 e to the minus b over 2m t sine. And of course there's other ways you could simplify this solution a bit. Just write it in terms of a single sinusoid if you wanted or whatever. But all I'm doing at the moment is writing out the homogeneous solution, right? This is the homogeneous solution to the problem. It is not actually a honest-to-goodness solution to the problem because it will not produce the forcing function, right? And also, as time goes to infinity, what happens to this, as we've discussed? Right. So this is sometimes called in the literature, in your textbooks, whatever. This is called the transient part of the solution x equals to xh plus xp, right? The particular piece we're going to find out is not transient, right? It's going to not go to 0 as time goes to infinity. So as t goes to infinity, x sub h of t goes to 0. All right, guys, so what is the particular solution that we should formulate here? So what should the particular solution look like here? I don't think we need the annihilator method for this one. Why? Because it's pretty clear that the homogeneous solution does not overlap with the forcing function, right? You can't, there's no exponential up here. It's not the same type. So there's no overlap. So I can just do the naive guess, which is xp is, well, actually, do you want to do things different for a change? We could use a complex, no, okay, fine. All right. Hey, there is a way to do this quicker with complex analysis. But anyway, cosine gamma t, I'll behave, plus b sine gamma t. If you use the imaginary exponential, you can cut the time of this derivation in like a half. But anyway, so xp is a cos gamma t plus b sine gamma t. And then, of course, we calculate our xp dot. We get ourselves a minus a gamma sine gamma t plus b gamma cos gamma t, and then xp double dot is minus a gamma squared cos gamma t minus b gamma squared sine gamma t, which if you tilt your head and squint, you should be able to see that that's minus gamma squared xp. It is certainly in our interest to make these kind of identifications as we go if they're there to be seen, because then when I make the next step of plugging the particular solution into the homogeneous problem, our life gets much simpler, right? So now if I go, okay, so m x p double dot plus b x p dot plus k xp equal to f naught cosine gamma t, right? I can look at that And notice that this xp double dot is simply that. So I have minus m gamma squared xp. And then I've got plus b times minus a gamma sine gamma t. Let's see here, plus b gamma cosine gamma t plus k xp. Well, I can do it up here. Equals to f naught cosine gamma t. All right. At this point, I'm going to go over there, see what I have. So I have k minus m gamma squared times xp. But xp is a cos gamma t plus b sine gamma t. And then I have my minus b a gamma sine gamma t plus b gamma little b, big B, cosine gamma t. Oh, I lost my gamma. Gamma cosine gamma t. I already got the xp term, and all that equals f naught cosine gamma t. All right. Excuse me. You guys follow me so far? I hope. So then what? What I would do next is I equate coefficients of sine and cosine, right? So I've got cosine gamma t terms, and I've got sine gamma t terms. From cosine, I've got a times k minus m gamma squared from this term, and then plus, is there a question? I keep hearing something. Equals to f naught, like that. And from the sine, I've got b times k minus m gamma squared. And what else do I have? This term here, right? So minus b a gamma, and what's that equal to? 0. So we got two equations, two unknowns, right? We're trying to solve for a and b. What should I do? You have many choices, right? Kramer's rule, multiplication by the inverse, many things. I think I'm going to multiply by inverse here. Was that a bad choice? What are we going to do?
I was going to
Add them? Add them. I guess I could solve. Oh, I think it's pretty easy to solve the second one for b, right? So this second one gives me b is equal to little b a gamma divided by k minus m gamma squared, right? You guys see that? And then once I know that, I can plug it into the first equation. What's that give me? What I call circular logic. Let's see here, but in a good way. So we've got a times k minus m gamma squared plus b gamma times a times big B, which is b a gamma over k minus m gamma squared, right? All of that's equal to f naught, right? So what we have then is a times k minus m gamma squared plus, apparently, b squared gamma squared over k minus m gamma squared equals to f naught. All right. And so what I have then, making a common denominator here, is a times, let's see here, k. I don't know if I want to do that, or do I want to make a common denominator? Oh, let me try. K minus m gamma squared plus b squared gamma squared, all divided by k minus m gamma squared equal to f naught. So apparently, a is equal to f naught times k minus m gamma squared divided by k minus m gamma squared squared plus b squared gamma squared. This is the time I check my notes. K minus m gamma squared over k minus m gamma squared squared base squared gamma squared. Yep. And then if we know that, what's b equal to? We had it up here, b a gamma over that, right? So when we multiply what we have here by, you know, this right here, we cancel the numerator factor of this, and we're just left with b gamma f naught with the same denominator. All right, so let's put this all together. xp is equal to, well, I've got a common term of f naught over that ugly denominator, k minus m gamma squared quantity squared. All right, plus b squared gamma squared. That's common to both of them. But then for the cosine term, I get k minus m gamma squared cosine gamma t, right? And for the sine term, I get plus b gamma times the sine of gamma t. This is again the time I check my notes before I invest any more effort into simplifying this here. All right. So at this point, I need to rely on one of the deeper results in trigonometry, which says that if you have, let me just write it as like a theorem over here somewhere. I guess I'll write it up here, theorem. Let me make it purple. If you have a1 cosine theta plus a2 sine theta, you can rewrite this as the square root of a1 squared plus a2 squared times the, well, you can pick sine or cosine. I think I'm going to go with sine for our current purposes. But yeah, sine of theta plus some phase angle. So, I mean, we could spend 10 minutes proving this if you wanted, but I think I'm just going to use it, right? So, And there are ways to understand this in terms of phasor analysis. If you guys have studied phasors, the imaginary exponential, and the interplay between sine, cosine, and e to the I theta, you can derive that using just like, vector geometry in the plane with complex numbers and such. But anyway, applying that here, what do we have? We have f naught, this thing just rides along, yeah? Over k minus m gamma squared squared plus b squared gamma squared, and then square root of this business here, k minus m gamma squared squared plus b squared gamma squared. Hey, that looks familiar. Oh, that's right, that's this. What do you know? And then sine of gamma t plus some phase angle, which we could find a formula for, but that's kind of beside the point here. The larger point is that after we simplify this, we can see what we have. We have, f naught over the square root of k minus m gamma squared plus b squared gamma squared times the sine of gamma t plus phi. So that's my, this is my not steady. This is the steady state solution. This is the part of the solution to this problem which is not going to go to 0 as time goes to infinity, right? It's just going to keep just oscillating up, back and forth, assuming Mr. Top Hat keeps pushing and pulling on the spring with friction, right? So what's the amplitude of the motion? It's this thing right here, right? This is the amplitude for the motion. If you double f naught, it doubles the amplitude, right? And if you change the frequency with which Mr. Top Hat's pushing and pulling on the spring, well, the amplitude changes as well, doesn't it? So how do we maximize the amplitude? May the odds ever be in your favor. Ask again. How do you maximize the amplitude? It has nothing to do with Hunger Games. I was just saying that for my own amusement. But anyway, yes. I mean, like, which gamma should I pick to make the amplitude biggest? Not one that's very small. Well, sometimes that's the biggest one. It could be 0. So without loss of generality, we only consider non-negative frequencies, because if you think about making gamma negative, that just corresponds to like rewriting the solution a different way. If I put 2 here, if I put minus 2 here, it's really the same solution. It's just been shifted by pi, right? So we can just consider non-negative frequencies. Usually 0 frequency is called a DC signal, because of its analog with, circuits. Nobody? How would I maximize the amplitude? You guys need to demand a refund of your Calculus 1. Who taught you Calculus 1? It wasn't me, was it? Okay, safe. Nobody? No one can tell me how to maximize a function of gamma? I mean, A is a function of gamma. We're trying to maximize it. It's a maximization problem, an optimization problem. What should I do?
Figure out where the derivative is.
Ah, finally, yes. Exactly. So what we want to do is look for the critical point. So we look for where dA, you just didn't want that to do what maybe the rest of you had it in your heart, and you just didn't want me to actually do that calculation because you saw what the differentiation was going to look like. Maybe that's it, right? Let's say that was it. But yes, if we want to maximize something, we use the first derivative test usually. So, and I guess it should be clear enough after we take the first derivative that we're getting a minimum or a maximum if we just think through it. But so let's do it. What is dA to gamma? Let's find the critical frequency. So we're looking at d to gamma of f naught divided by the square root of k minus m gamma squared squared plus b squared gamma squared. And by the way, it almost never pays off to multiply these things out. It's almost always better to leave them unmultiplied and maintain that special form, because it will make the calculus eventually, yowzers, go nicer. Uh-oh. All right, so the f naught's a constant. That pulls out. And we have ourselves a minus 1/2 f naught. I'm tired of writing this, so I'm going to give it a name, Pac-Man. What was that?
How about fiend?
How about what?
Fiend.
What?
Fiend.
I don't know what you mean.
F-E-I-N. Fiend.
No. That's some kind of Zoomer joke. Let's see here. Let's see here. So we've got Pac-Man to the minus 3/2, right? Times, well, the derivative of Pac-Man, right? Which in this case is d gamma of k minus m gamma squared squared plus b squared gamma squared, which is minus f naught over 2. I'll move Pac-Man downstairs, give him a positive exponent, make him feel better. I don't know. I'm not sure how Pac-Man really feels. That's 2 times k minus m gamma squared. Then chain rule says times minus 2m gamma, finally, to the end of the derivative of that, and plus 2b squared gamma. All right. Now, can Pac-Man be 0?
Yes.
Yes. I'm going to say no. Well, I guess if k and m and b were all 0, then yes, right? But physically speaking, we don't want to think about that, right? I don't know what a massless spring, I don't know what a spring on a mass, like if the mass is 0, I don't know what to make of all this, right? Newton's laws break down for mass 0. We had to wait for Einstein to talk about that. So like m is non-zero, well, k is non-zero too, otherwise it's not a spring mass problem, right? So if you look at this, I think it's fairly clear that this is not equal to 0. So that means that if there's going to be a critical frequency, it must be from the thing in the square brackets being 0, right? So if we set this equal to 0 to look for the critical frequency, we've got an equation here, minus 4m gamma times k minus m gamma squared equals to minus 2b squared gamma. I guess, oh, okay, so this says what? Either gamma equals to 0, that's one path, so what's the other path? Gamma not equal to 0. If gamma is not equal to 0, we can divide by gamma, right? And when we divide by gamma, we get what? We get minus 4m times k minus, m gamma squared equal to minus 2b squared. But this gives me k minus m gamma squared is equal to b squared over 2m by algebra, which then gives me m gamma squared is equal to k minus b squared over 2m. And then if I divide by m, I get gamma squared is equal to k over m minus b squared over 2m squared, right? And so I'll write it over here big. So we get that the critical gamma is either equal to 0 or what? Or it's the square root, because we take the frequency to be positive without loss of generality here, k over m minus b squared over 2m squared. Or if you want to write it in terms of the natural frequency, it's the square root of the omega naught squared minus b squared over 2m squared, I think. See, because the, oh, maybe I'm wrong about that. Never mind, that's not the natural frequency here, because it involves the b. My bad. Well, that would not be the same omega naught I introduced earlier. Let me fix, this should not be called omega naught. I think this should be called like, I don't know, we'll just call it something else. Let's just call it omega 1. I think omega naught is the other thing. Sadly, I was too lazy to bring my book with me. So well, I just call it omega is the natural frequency in the notes. But this is in section 4.10 of the textbook. All right. So there you go. This is the frequency that we should choose if we want to maximize our response for the spring. All right. What's probably a more physically realistic and interesting example is if I take the same example and do it for an RLC circuit. See, because this problem has an analog. What's the analog in terms of RLC circuit analysis? The RLC circuit analysis analog of this is you've got, you know, E naught cosine gamma t, and you're trying to maximize like the voltage, I think, or no, the current. Yeah, I don't remember what I'm maximizing, honestly, at the moment. But R, L, C. So this, that circuit, you can also ask the question, like, when do you maximize the, you know, well, I can't, off the top of my head, I don't remember if it's voltage or current that I'm maximizing. I mean, the, I'm trying to remember what, oh goodness gracious. Well, let's look it up. I think it's current. I mean, maximizing the amplitude of the current is going to maximize the voltage across the resistor, for instance. I know that. I have this worked out in the notes. Let's look at it. So I was tempted to ask you guys a take-home quiz over the weekend about this. Not that I'd expect you to do this calculation from scratch or anything. That's not what I mean. I mean, like, just to like apply it, find the actual critical frequency for a specific physical system, right? Because once we've gone through this trouble together, we have a formula, we can use it, right? Like, when would the DC frequency be, like the zero frequency, be the correct answer here to maximize the amplitude? Does this have to be real? No, I mean, we're taking something minus something else, right? It could be negative. And in this context, this has to be real for this derivation to hold. So basically what that shows you is if you're in the situation that k over m is less than b squared over 2m squared, then to maximize the amplitude, you just use a constant force. You use the zero frequency solution. So that's where that comes into play. So I mentioned at the start of all this that it was way easier if we use an imaginary notation. And then you guys are like, no, don't do it. Because you know my ways. But that's okay. Here's, excuse me, the solution. We just went through all this. And there it is. This is a typo right here. I'm not sure what happened here, but that's a typo. I think that's supposed to be divided by m. Somehow it escaped the square root. But here's the corresponding RLC problem. So we've got LQ double dot plus R dq dt plus 1 over C times Q equal to the voltage applied. And the thing is, okay, so that finds me the charge as a function of time, perhaps on the capacitor. And then if I differentiate that, that gets me the current. But I think the maximum charge on the capacitor is going to maximize the current as well. So I don't think these are separate questions. But anyway, here's the complex way to solve this. So the way to solve this with complex, which is worth thinking about for a second, is if we have like cosine gamma, V naught cosine gamma t, that is the real part of V naught e to the gamma it. See, because e to the gamma it is cosine gamma t plus I sine gamma t. So the real part of this is our given voltage. So what I do is I take the problem I'm given and I complexify it in the sense that I allow myself a fully complex solution. And I make it such that the fully complex solution, the real part of it, is going to be the solution I'm interested in. He was like, well, why are you making the problem more complicated to solve it? Well, because if you use complex notation, your particular solution looks like this. A e to the I gamma t, where A is a complex constant. You differentiate that, you get I gamma A e to the I gamma t. You differentiate twice, you get minus gamma squared A e I to the gamma t. You plug it in, you get this, you get that. You've solved for it in, like I said, half the time. Now, there are strings attached. A is a complex constant. So you get this, which then you have to multiply by the conjugate of the denominator, which gives you this formula here. And you can start to see the same patterns appearing, right? 1 minus a squared squared plus a square. It's the same pattern. And of course, we could just run our previous calculation straight through the dictionary that I wrote down the other day that transfers you from the world of spring mass problems to the world of RLC circuits. We could just do that, but I think it's more interesting to look at this calculation together. This is not part of the required part of the course. You could use it if you use it intelligently and correctly. I will let you I'll give you credit for it. Heck, I'll probably give you a bonus point. But so let's see here. This is my A. This is the amplitude that I found, and that's e to the I gamma t. And then the real part of this is the solution to the problem, because of the way real and imaginary parts behave. So we actually, from this, I get that QP1, which is this, and I get a QP2, which is that. Now QP1, if I plug it in, I get the forcing function V naught cosine gamma t, whereas this one will give me V naught sine gamma t. So it's a twofer. If I do this calculation, I solve not just the cosine problem, but also the corresponding sine problem. Cosine from the real part, sine from the imaginary part, both at once. Almost the same trouble. The additional thing that would make this troublesome for students, perhaps, is this step here where I have to, make the denominator real. But anyway, so lo and behold, oh, that's pretty much it. So anyway, after that, it's the same calculus. So, all right, let me see if I got anything else we can look at here. Nobody wants to look at physics. Let's see here. No. I feel like I had So like, here's test 1 from yesteryear. I've recycled some of these problems as your homework and stuff. So this we've already gone past, right? Like this was on test 1. Test 2 is on what? Mostly material after test 1, right? Yeah. So let's see here. So I think like this was on your, this was in the thing you guys just worked out, right? Find the real solution of y prime prime plus 4y prime plus 13y equals 0. So we write down the characteristic equation, complete the square, and from that I directly can read lambda is minus 2 plus or minus 3i, and that implies I get this solution. Right, now assuming x is the independent variable, like that. Ooh. What else did I have on here? Homogeneous solution. Here's one I didn't put in your take home, but just to give you an idea of one way I can test the annihilator problem. I do this sometimes because it's just easier for me to grade. I'm like, here is, you know, I've got d to the 4th plus 9d squared y equal to x plus cosine x. I say it can be solved by the method of undetermined coefficients method aided by the annihilator method. Find the minimal particular solution. All right, so here's the deal. To kill off x, I have d squared. To kill off cosine, I've got d squared plus 1. When I annihilate my given differential operator, I get a common d to the 4th. I get d squared plus 9 from factoring, and d squared plus 1, right? Which gives me this general solution, but this piece and that piece are the homogeneous. So I just have this and that for my particular, which makes me pick this one. Right? So this is a format that I kind of like to test on whether or not you understand the annihilator method, because it helps me not have to like gouge out my eyes from trying to figure out what you did. It's quite horrible sometimes to figure out what just happened, you know. And some of you, do you guys watch Boruto?
Naruto?
No, Boruto.
Oh,
The new one.
sequel one? The one sucked.
Yeah, some of you guys like do with your writing what he does with the Rasengan. See, that joke has a limited audience, but I feel like you're writing part of your solution on the paper, but the other solution, part of the solution is like in another dimension. It's hidden to my eyes, but it's there somewhere, maybe like transverse to the paper. Like, I don't know, you can see it, but I can't see it. I don't know. I'll shut up. So another example I think you guys just solved was this one. So this is simple enough because it's, again, so there's, you know, the homogeneous solution has no sines and cosines in it, which means we can just use the naive method, right? If I don't say use the method of annihilators, you don't have to, right? So part of this course is understanding what tool you need to use for a given problem. You have to recognize your enemy, right? This enemy does not require an annihilator method. It just requires plain old naive particular solution. Work it out. Yeah.
So you could use the annihilator method on this. It would just be.
Sure, but then you have to work to get to yp equal to that. You know. Listen. So if you choose so suppose you don't realize you need to use the annihilator method, right? And you make the wrong guess for yp. What's going to happen? It's not going to work, right? You're going to get 0 equals to 1 essentially in the algebra. What do you do then? You just go, oh, well, go on. They give you partial credit. I mean, that's one approach. But a better approach would be to think about your life and think about where you went wrong and adjust your answer and redo the problem and not give me those points. Like, that would be better. I have got enough points. I don't want more. So, you know, and in that kind of situation, maybe the correct approach is to draw a single line through your work and say, this is wrong, I'm working it on the back. That way, if in the middle of this process I call time, you don't have 0 partial credit from that, you know? Just a thought. All right. Let's see here. Anyway, I'm going to go over the solutions to the mission on Monday. Do you guys have any questions before the weekend starts? Yeah.
How do you know when to use the
Oh, how do we know when to use the annihilator method?
The variation of parameters.
I'm an idiot. Yes, variation of parameters. So, I mean, I can give you a very unintellectual answer, which is if it's secant, if it's tangent, if it's 1 over t times e to the t, if it's 1 over x squared times e to, I don't know about that one, e to the x. If it's anything which is not in our list of possible solutions to the homogeneous problem, what are those? Polynomials. That appears from lambda equal to 0 multiple times. Pure sines and cosines comes from lambda equal to plus or minus I times a number, right? Sines and cosines times exponentials comes from complex roots, right? Exponentials just comes from pure real roots. T's times exponentials, or t squareds times exponentials, comes from repeated roots. If it's not one of those things, or a sum or product thereof, you have to use variation of parameters. What's my major advice for variation of parameters? Take time to carefully calculate the Wronskian. Calculating the Wronskian and simplifying it before you do the integration is mission critical. The Wronskian must be non-zero. We have proved that the Wronskian is non-zero for a solution set. If you simplify you quote-unquote simplify your Wronskian, but it's got 1 minus t times e to the t, you're wrong, because that can be 0 when t equals to minus 1, which is not possible. The Wronskian is either identically 0 or identically non-zero for a solution set. So your Wronskian has to simplify to something like a constant or an exponential, pretty much. Or t squared plus 1, something like that. Something that's non-zero. Anyway, I shut up. For real values, of course. We keep it real in here.